that orientation. Okay, I did not tilt it. The y prime and z prime were given.
Yeah.
Okay, I did not tilt it. But all these moments, okay, the moment over here and the neutral axis over here are measured from where? From z prime axis.
I'll look at it after. I'm still lost.
Okay.
Don't worry. It's all good. I don't want to
So,
hold that up.
so just remember everything, the orientation of the moment. Okay, I'll write this. I think this is important. Orientation of the moment okay, of moment vector and neutral axis are from the z or z prime axis, okay, which is attached or which is fixed. Let's not use the word attached. Fixed to the structure. Okay, so for this problem, the z prime and y prime orientation, okay, is at that orientation. Okay. In example 2, below the green line is tensile and above is compression. Above, so in this example over here, anything that above the green line is compression. Okay. Above the green line is, yeah, you're right. Above the green line is compression. Zihan, you're right. Okay. Right. Any other question before I go on for the next topic? Or not the next topic, but the next it's still pure bending. Okay. So the next section that we are going to look at is known as eccentric symmetrical bending. Okay. So I have briefly talked about eccentric symmetrical bending before on last Friday. Okay, so now I go into more detail, and there's one thing that I want you all to learn that is very, very important. Okay, so I'm going to again use another diagram. Okay, so this sort of configuration is where we have eccentric symmetrical bending. So how this eccentric symmetrical bending is different from centric. What we learned before was centric. Okay, so let's look at the difference first. Okay, so if we look at centric symmetrical bending, we only have one formula, which is stress x, stress in the x direction. Okay, so I'm going to draw my orientation relative to this diagram. So this is x, y, this is rotation about z. Okay, so for centric symmetrical bending, you have stress x is equal to mz or mz, yep, over izz multiplied by y. Okay, this is centric. So if it's centric, it's just induced. This is just induced by bending moment. When we call eccentric, symmetrical. It's still symmetrical, okay? Because why is it symmetrical? Because the moment is only applied in one direction. Okay, symmetrical because the moment is applied in one direction. So all we have now is stress X is equal to P, okay, Px divided by A, right? Now by right, the formula should include a minus down there. Okay, I'm going to obey the formula. Okay, but later on, whether is it plus or minus, okay, we look at our moment vector. Okay, it works with the moment vector. So this is equal to mx over a minus mz over izz by y. Okay, and we classify it as eccentric is because under this configuration that you see, right, there is a moment vector, or there's a moment applied at point C, and then there's a force, axial force, also applied at point C. Okay, so over here, this load over here is induced by axial force. Okay, over there is induced by the axial force, and then over here it's induced by bending moment. Okay, now question for you guys: why did we analyze point C? Why are we so fixated about point C? Anyone?
Is that where it's going to break first?
Where it breaks?
Bang on. Okay, we are so fixated about point C. You're right, Tyler. Also, it's because this is the location where failure will occur. Okay, that is the orientation for where failure will occur. Okay, so a lot of times, okay, a lot of times, but before I tell you guys a lot of times first, now the moment, okay, so how to calculate the moment? So mz is equal to p, right, is equal to the load p prime multiplied by d. Okay, and if you look at d, okay, so d is the distance between the applied force to the centroid. Okay, to the centroid. Now, a lot of times, now this diagram is really, really important. Okay, I'll tell you what. A lot of times, we tend to forget. We did not forget about the moment. Okay, we know that because over here you have P times D, you have a moment over here known as M prime. Okay, so this M over here is a counter moment. The moment we will not forget. A lot of times we tend to forget when we have P prime over here, we need to have an F in the opposite direction. So M prime and M, P prime and P, and F is due to we apply Newton's what? Third law. Okay. Action equal to reaction. Same in magnitude, different in what? Different in direction. Okay. So when we sketch this out, okay, when we sketch this out, okay, when we sketch this formula out, so let's say we have a cross-sectional area. Okay, so I'm going to draw. Okay, so let's say now we view this in a different orientation now. Okay, so now based off what I've drawn, this is now our y, and this is our Z, and this is rotation about X. Okay, so everything is relative. So this is where we have our centroid. Okay, so this is our centroid. Remember, I call this centroid, yeah, not neutral axis. So if we were to sketch stress X is equal to Px over A. Okay, so A is the cross-sectional area. Okay, so this will be our Y. Okay, so this is our 0. So what we'll see down here is where we have Px over here, A. Okay, so everything over here, no, not so far up, it ends over here. Okay, so this is how we sketch our stress distribution. Okay, so this is where we have our Px over A. Okay, and then now we were to sketch our bending moment. So stress X is equal to minus mz over Izz multiplied by Y. Okay, give me another 3 minutes, I'll be done. So again, this is our Y. And based on this orientation over here, we know that at the top is going to head of the moment vector is going to be compressive. The tail end is going to be what? Tensile. Okay. So our moment diagram now looks like this. Sorry, our stress distribution. It looks like this. Right. So I taught you guys how to draw compression, tensile. Okay. And then when you add the both of them, okay, and when you draw the normal stress, okay, so this is equal to stress X is equal to P over A, Px over minus mz over Izz divided by Y, multiplied by Y. So if this is my Y now, okay, we know that there'll be a shift. So the gradient will still be the same. Okay, there'll be a shift. Okay, so this is initially, and then there'll be a shift. Okay, so this is now over here. This is your compression, and this is your tensile. Okay, and the position of the neutral axis now have shifted. Okay, so this is the position of the neutral axis. Okay, now before I let you guys go, I have another 2 minutes of your time. Which one will induce a higher stress? The axial loading or the bending moment? Anyone? Which one will induce a higher stress? Let's say the applied load is the same. P is the same. Anyone?
The bending?
Why do you say that? You are right, but why?
It just seems greater, and then it's like twisting it at the different ends. So like those are going to be like weaker and easier to snap with the way the force is distributed.
So Matthew, you're right, okay? So the way to demonstrate is this, okay? If you were to pull your ruler, is it easy to break your ruler? Yes or no? It's difficult, right? if you bend your ruler, is it easier to break your ruler when you bend it? Bending is easier to break your ruler, yes or no, than to pull or to what? Compress. Okay. So I want you all to remember things this way. Okay. Not to memorize stuff. You have to be physically able to relate the stress field that you calculate. Okay. I want you all to have that confidence. Because I have that confidence, I want you all to have that confidence. Okay. So what I'm going to do now, I'm going to stop the lecture here. Now I'm going to I've already posted the homework, but there are some questions that you all cannot do yet. Okay, so I'm going to get rid of some of the questions. Now, your quiz is due this evening at 2359. Only about 50 students have done it. Please try to complete the quizzes, okay? If that's the case, have a great weekend, and I'll still stay behind for questions. I'm going to stop recording first, okay? I'm going to answer the question asked to me by Nicholas.
Sir, could you just zoom out a little